Bam, here is our second part of this trig review stuff. I'm going to be going over radians as well as starting on question 12 in that packet after the mini lesson's done. So if you feel like you don't need the lesson, want to jump right into the problems, go ahead and do it. But we're going to go ahead and start out where do radians come from, what are they, all that kind of stuff. But before we do that, we need to start off with 360 degrees, the degree symbol. What are degrees anyways? Where do they come from? So to understand that, we have to go way back in time. Ancient Babylonia, how they counted. They counted in the most interesting way. This is how they counted, and they were able to count up to very large numbers on their hand, and then they tied this into their religion, and they tied it into their understanding of the world around them, because effectively they found out, or they estimated, that the Earth went around the sun in 360 days around the sun. They also had a special holiday towards the end of the year where the sun, quote unquote, stood still in the sky. It's the equivalent of, oh man, I don't even know if it's the equinox or the solstice or which one it is. This is why I need to do a little more research before I start these things. But the point is, they thought there were 360 days around the sun instead of what we know today is correct, the 365.25 or whatever it is. This is how they counted, though, and this is why they got to 360, and how they thought it all was connected to their religion. This is what they did. So they would kind of curl their hands a little bit, and then they would count with their fingers, and they would say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But when they got to 12 here, that's when they would put a 1 up on their finger, because they were effectively using this as a base 12 momentarily. So now they're at 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. But again, once they got to 24, now they have two 12s on their finger. So they have these two 12s. Two 12s, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. And now they have three fingers for 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48 for 4, and then 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, and then boom, a full hand was 60. And then the idea is because you can maybe use somebody else or your feet or some other idea, is if you use an additional 5 fingers for this process, you could actually get all the way up to 360 just by counting on your hands. And this was a way to divide a circle into 360 parts. Now, you might be saying, what in the heck, why in the world would we still be using this all the way later today if that's how it is? And it turns out it's because 360 is just a wonderful number. I forgot the exact name for it. You can look it up on Wikipedia if you want, but it's something like a hyper-divisible or a super-divisible number. But this guy is divisible by so many things. You can divide it by 2, 3, 4, 5, 6, 8, 9, 10, 12, 15, 18. There's just 20. It goes on and on and on about how many different numbers, 24. You can divide it into so many different numbers. And because you can divide it by so many numbers, it's super useful to be able to divide a circle into that many different parts evenly. And that's why it's stuck around to today. And in fact, there are still people who use the degrees, minutes, seconds navigation system, mainly all pilots and all ship navigators and things like it. They still use this 360. However, ultimately, it is arbitrary. It's also not even right. 360 around the sun, we already know it's not right. But it's just useful. And because it's useful, it's stuck around. But being useful doesn't make it mathematically useful. So we have to develop something different for things to hold up in the mathematical sense. So instead, we kind of just delete degrees entirely, and we say, nope, we don't agree with degrees at all. And instead, we're going to jump into a different definition where we start off by defining a radian. Now, a radian, what it is, we define 1 radian to be the angle measure when arc length is equal to the radius. Now, I am not going to be able to draw this perfectly, but I'll do my best. The idea is that around right there, there's this part. If I were to kind of make a circle out of this thing, you could actually finish the entire circle. going all the way around if you really wanted to. But the idea is there's some angle measure, which we again will call theta, where whatever that angle measure is, this length here, this radius, will be the same as this curved length out here, and this will also be a radius. Anytime where that is true, then we would say that theta is equal to 1. Now, what this does for us, will be able to let us rigorously define all kinds of different pieces of information. We'll eventually tie it back to sine and cosine. I'm going to take a quick drink of water. And yeah, it's kind of where we're going. Just so you can kind of have a better visualization than my little random drawing here, I did prepare by stealing from Wikipedia this cool thing here. So it's going to go ahead and draw a full circle for us. There's a full circle, and there's our radius. And then, oh, it didn't actually go. I got to restart it. Oh my gosh. Okay, here it is. There's that full circle. There it is. You can see it. And yeah, so we're drawing it around, and they're bending it down to create the 1 radian angle measure, 1 rad they use for a radian here. Then they're going to extend it. Now they have 2. Now they have 3, and they have that little sliver that's not quite there, and the remaining part is the 0.14. Half a circle is pi, and if you go around the entire dang circle, we're going to end up with 2 pi radians. So super duper useful little picture there. That's kind of the idea. And what that leads us to is that because 2 pi is a full circle, we would say that 2 pi radians is equal to 360 degrees. But if you notice, I didn't even write rad. That's because radians are unitless. That will matter more in a physics class. But if I were to divide both sides of the equation by 2, we're going to get pi is equal to 180 degrees. And we're going to be using this quite a bit. Basically, to convert from radians to degrees, you're always going to need, so if you're going from radian into degrees, you're always going to be multiplying by 180 degrees divided by pi, whereas if you're going from degree into radian, that means you'll be multiplying by pi over 180 degrees. Now, the way I remember this is I want my little degree symbol to cancel out if possible. So it's going to be the degrees on the bottom when you're multiplying to get into radians, then vice versa. You want the degrees to show up. You want to divide by the pi, and that's kind of how I remember it. The other part of this is also shown in that GIF that we just did, but the idea is we are now going to start making all of our measurements starting from the right-hand side of the x-axis for all angles, and we always go counterclockwise. So all angles are going to start here and go around. Let's do our best to start these problems now. All right, so here we go. Problem number 12. Convert each degree measure into radians and each radian measure into degrees. And for some reason, it is all degrees. It's supposed to have some radians to go into the other ones. That's a little bit sad. It has nothing going the other direction, but you know what? Life's going to go on. I must have misclicked when I was creating this assignment. All right, so we have 915 degrees. So we're going to go ahead and take it, and just like I wrote on that previous page, when you're going from degree into radian, you multiply by pi over 180 degrees. And here's the thing, though. If I were to type that directly into the calculator, you're going to have this problem where the calculator simply gives you a whole bunch of decimals. So because of that, what you're going to do is when you type into the calculator, use a 1 instead of pi when you're doing this in the calculator. That way, you're treating it kind of like if it was like a variable almost, even though it's not a constant. You're treating it like that constant. They're treating it like variable. When you do that, the calculator will not mess up. So let me show you what I'm talking about. If I go 915 and I multiply by alpha y equal enter, there's that fraction button again. If you are new to seeing this, that's alpha y equals, and then the enter button on the calculator. But if I were to type in pi and then divide by 180, I get this decimal number that is not that useful to me. It turns out that 915 degrees is 15.96 radians, which is not actually that useful because we want to be able to use it in pi so we can accurately divide the circle into parts. So instead of having a pi there, we're going to put a 1. And if we put a 1 there, we get a nice 61 over 12. And that's going to be the number that we want to deal with. So we're going to say 61 over 12, and then we throw a pi afterwards. And that's the answer we're looking for. We do not want that decimal answer. Continuing on, you do exactly the same thing for every single one of these. They're really, really straightforward. There's not really a lot of thinking involved. It's just multiply by that 1 over 180. And that's why I really want to make sure I had different versions of it. You get 32 over 9 here. And yeah, just do the same exact thing over here. I'm also going to need to insert a negative sign. So insert that negative sign, and now it's 570, negative 19 over 6. And last but not least, same exact thing, but I know this one off the top of my head. This is one that's recommended to memorize is pi over 6, or 1. You could also have written this as 1 over 6 pi, but I always like to replace the 1 with a pi if you can. All right. So the next part, draw an angle with a given measure in standard position. So 130 degrees, we should know from our geometry classes and just previous life experience that corners create right angles 90 degrees. So this part right here is 90, and the remaining part is going to be 40 more. So 40 more will be about right there, and it always comes from over here. Now, this one might be a little bit more difficult to deal with. There are two ways to think about this. Here's the way that I prefer to think about it, is we remember that 2 pi is a full circle. So because 2 pi is a full circle, and we're looking at fractions of pi here, we could do a little multiplying by 2 over 2, the old fraction stuff, and then therefore we'd say that 4 pi over 2 is that same exact full circle. So what we're going to do is on this problem is we're going to go ahead and say that we're going to go around. It's a negative, by the way, so we're going backwards. But if we go around all the way up to this point here, if you've gone this far, you've gone 4 pi over 2, and we have 1 more pi over 2 to go, half of half a circle, which is going to bring us to right here. So there is our angle in standard position. The other way to think about this is instead to use our calculator, and just like we were saying before, you type in the negative 5 pi over 2. So negative 5 and alpha y equals, negative 5 over 2. Again, we don't need to type in the pi, multiplied by 1 over 180. But this time it's going to be 180 over 1, so I didn't even need to put the fraction, but I did anyways. And you get negative 450 degrees. So if we're doing negative 450, okay, where the heck is that? Well, it's more than a full circle, right? It's more than the plus 360 that we had, and there's that negative 90 that we have as a leftover portion. There are other ways to think about this, but I do think that those are probably your best options there. Let's continue on. We have another concept here that we have not talked about yet, the corresponding quadrant and reference angle. So let's go ahead, grab another sheet of paper here, and just talk about this stuff. So the quadrant parts are very easy to do. You just kind of learn them right away. For some reason, all the mathematicians I've ever seen always use Roman numerals for their quadrants, so I guess I will too. But because we start off here and go up, our first quadrant is right here. So we have that Greek letter 1, Roman numeral 2, and then 3, and then 4. Quadrants 1, 2, 3, 4. And just in case you can't read those, that's 1, 2, 3, 4. So that's what they're talking about when they talk about the quadrants in there. And then after that, they talk about what is called the reference angle. So the reference angle, I always call it as theta star is your reference angle. And you get it by finding the angle from x axis is the angle from the x-axis regardless of where you are. So what that means is, I'm going to go ahead and make this pink, by the way, so this is all going to be pink for me here. But no matter where you are, there are 4 places you could be. You could either be in the first quadrant, the second quadrant, the third quadrant, or the fourth quadrant. But if I were to go towards the x-axis from these lines, so I'm going directly towards the x-axis, directly towards the x-axis, directly towards the x-axis. Any of these that go directly towards the x-axis, these are all going to be my theta stars. By the way, theta star is kind of my own made-up thing. I've seen some other books use similar notation or something like it, but that's just my own thing. So if you say theta star in the future, the teacher's like, I have no idea what you're talking about. They're talking about a reference angle, or you are anyways. But if you notice, that's not the regular angle. Like the regular old angle is always coming from the right-hand side. So there's our regular angle. There's another regular angle. There's another regular angle. And oh my gosh, all the way around, there's our last regular angle. So because we have all these 4 different possibilities, the reference angle is simply what is left over. I prefer to simply memorize which one is which. In this thing, theta star is always equal to the original theta. So the first quadrant's the easiest one. You can see that this angle here and this angle here are identical. But for the second one over here, we have this full top here, creates the whole thing, but we just want what's left over. So what we do is we do 180 degrees or pi radians, and we subtract what's left over. So we would go ahead and say that theta star is equal to, depending on the situation, either 180 minus the original theta or pi minus the original theta, depending on if you're in degrees or radians. Likewise, the same exact concept here on this one. If I go all the way around, well, that's going to be pi or 180, and then you're adding this little tiny bit left over. So you'll have theta star is equal to 180 degrees plus the theta. Wait. What am I saying? I need to subtract 180 degrees. Oh my gosh. Mr. Richards, what are you doing? Taking theta and you're going to subtract 180 degrees, or you're going to take that theta and you're going to subtract pi. My bad for writing the wrong thing the first time. And then the last one here, our theta star, you're going all the way around the circle, but you're missing that little tiny part. So what you're going to do is for this one, theta star is going to be equal to either 2 pi minus your original theta, or 360 degrees minus your original theta. And that will help you find your angle if you want to do it strictly memorizing, or you could actually just draw your picture out every single time. Either way is going to kind of work for you. So again, 1, 2, 3, 4, and then the quadrant rules. There you have them if you'd like them. Boom, boom, boom. Continuing on. So draw the corresponding quadrants and reference angle. So we need to figure out where this 5 pi over 6 is. It's a little bit less than a full 6 over 6. 6 over 6 would be at the halfway mark. So it would be like all the way over here. It's a little bit short, so it's going to be about right there. So this is going to be our 5 pi over 6. The reference angle is this part that's left over. You could use your formula, or you could quote unquote complete the pi, which is going to be pi over 6 here. It's going to be what's left over. So theta star, we would say, is pi over 6, and it's in quadrant number 2, is going to be our final answer here. 275. 275, drawing that one out, we know we have 90, 180, 270. We're a little tiny bit more than here. So here's our original theta, and our theta star is going to be our 360 minus that 275, which is going to be 85 degrees out in quadrant number 4. Beautiful. Pausing really quick, take a drink of water. All right, we're on to the next page here. Only a few more problems left on this video. So find the measure of each angle. So finding the measure of each angle here, remember going up is going to be a positive value. Going down is going to be negative. So this one's guaranteed to be a negative number. Then we just need to figure out what negative number it is. Well, it's a little bit more than 90. This is 85 here. So this part right here, that little sliver, is 5 degrees, but we're looking for the whole thing. That's going to be negative 95 degrees for our final answer. And then here we go for this one. This one's going to be a little bit tough. So we have to go all the way around. That right there, remember, a full circle is 2 pi. So we have 2 pi plus. And then we're going to go all the way around again. So we have another 2 pi plus, and then whatever's left over. To figure out what's left over here, we do have to do a little bit of actual fraction work, a little bit of old school stuff here. We have pi over, the full circle is pi. So this little section right here, this would be pi over 2. That's half of half a circle, or 90 degrees. And we're doing pi over 2, and we're subtracting that pi over 3. You can just use your actual fraction work if you wanted to and write 3 pi over 6 minus 2 pi over 6 and do that conversion. But remember, you can use your calculator and use ones instead of pi's. So 1 over 2 minus, it's going to be 1 over 6 in the end, but 1 over 3, maybe. If you could do that in your head, great. You get 1 over 6. Anyways, it's going to be pi over 6. We have all these guys together. 2 pi plus 2 pi plus that pi over 6. So using our calculator, 2 plus 2 plus that 1 over 6. And I could have just copied it from above. And you'll get 25 pi over 6. Oof! Dang, we did it. All right. So this next part, we have not quite gotten to this part in the lesson. So yet again, pause and grab a piece of paper. All right, so second part of this is going to be called reciprocal functions. So we had sine before, but if we take sine of theta and we instead convert it into 1 over the sine of theta, this is called the cosecant. And I'm going to write out the whole word the first time. It's the cosecant of theta, which we abbreviate as CSC of theta. There's a similar idea with cosine. If we took the cosine of theta, that ends up being instead 1 over the cosine of theta for this one, which is going to be the secant of theta, which is really SEC of theta. And that might be a naming convention that's super annoying to you because you're thinking, shouldn't sine go with secant and cosine go with cosecant? Unfortunately, the answer is no. The reason for that is much more clear once you've done a little bit of calculus work and maybe a little bit more higher level stuff. I don't have a great reason for you for it now. Maybe somebody in the comments knows exactly why that is without using any calculus ideas. But there's a strong reason for it once you get to calculus. It makes a lot more sense then. But for now, it's going to be just that's the way it is. Luckily, tangent is the easy one. Tangent of theta does become 1 over the tangent of theta for the reciprocal function, which is the cotangent. So that's what we're using. That's what we're using. Cotangent, which we are going to write as cot of theta. So this is going to be our 3 reciprocal functions. By the way, since sine, or the SOHCAHTOA situation with opposite over hypotenuse, this one is going to be the hypotenuse over the opposite. This one's going to be our hypotenuse over the adjacent. And this cotangent of theta is going to be the adjacent over the opposite. So it's like the reciprocal, the upside down version of it. The other thing that we're going to need for these problems that we haven't quite talked about yet are the signs of sine, cosine, and tangent. In order for us to do that correctly, we do need to understand a little bit more than what we were doing before, and that is the idea is whenever we have an angle, so for instance, if we have the sine of some theta, we're used to using it as a triangle. We're always going to be doing the sine of the reference angle instead. Every single time, that's what we're going to be doing for all these questions. But we're going to do the sine of the reference angle, but consider the quadrant. Consider the quadrant. What I mean by consider the quadrant is this. If you were to draw, say, let's say I wanted to try to find the sine of 150 degrees. Now, you can't just straight up do the sine of 150. I mean, you can if you know what you're talking about precisely. If you plug it in your calculator, for instance, you'll be told that this is going to be a 1/2. But how can we do this? How do you actually do this? Well, draw a little picture for yourself. You have to figure out where 150 degrees is. So 90 and a little bit more, just like that last page, is going to be over here. But what we're going to do is we're going to say we're going to consider the quadrant over here. For the sine, we're always looking at for the theta star. That's our theta star over there. And the sine of that one is going to be the opposite over the hypotenuse. So we simply have to figure out some triangle that has this guy over here where we have a 30. Hopefully remember our 30, 60, 90 triangle from way back then. 30, 60, 90 triangle's got a 1, a square root of 3, and a 2. And because of that, we can simply say, hey, I know that this guy's got to be a 1/2. But what if it was a different one? What if it was going down instead? Well, because this was a positive going up, if I instead looked at something like the sine of 210 degrees, which would be very, very similar, instead it would be over here. So because we have 180 plus a little bit, this is still 30 degrees, and we still have this 30, 60, 90, but now instead of being like positive 1, this is effectively a -1 because you're going down, which makes this one going to be a -1/2 instead. So because there's that -1/2 idea, you can have positives or negatives. There are a few ways you could do this. If you want to, you could just draw the picture every single time, and then you can just look at the actual physical signs of the things, because you could say, hey, like my y value is negative, my x value is negative, and because of that, I know that sine's going to be negative, cosine's going to be negative, and tangent's got to be positive. You could just draw the picture separately every time, but the preferred way of doing it is the mnemonic device of all students take calculus. So if you have the mnemonic device of all students take calculus, it'll help you remember which ones are positive and where. All three, sine, cosine, and tangents, are all positive. So positive sine, positive cosine, positive tangent over here. But the students is the sine quadrants. That is to say, you have a positive sine, but a negative cosine and a negative tangent. The all students take quadrant, the T quadrant, is going to have a negative sine, a negative cosine, and a positive tangent. And then the calculus for cosine, you'll have a negative sine, a positive cosine, and a negative tangent. And that's kind of the idea that you're going to be using throughout this entire dang last page or last thing for this video. Find the exact values of the 5 trigonometric ratios not given. So you have the cosecant is going to be 13/5, just like we were previously talking about. That means that the hypotenuse is 5, and the opposite is, or the hypotenuse is 13, and the opposite is 5. So we have to draw any old triangle that has the situation. It doesn't matter exactly where you put it. But you're told here that you have a 13 for the hypotenuse, a 5 for the opposite. We hopefully have memorized that one from the previous video as a 5, 12, 13 triangle. But you're also told that the cosecant is positive and the cosine is negative. And I just put this on the floor, I don't know why. But if you have a cosecant, which goes with sine, if sine is positive and cosine is positive, the only place where sine and cosine are positive is here, which means that all of our answers are positive the whole way through. So we can go ahead and write down our sine of theta equals our cosine of theta equals our tangent of theta equals, and then we're going to have to figure out the cosecant of theta equals the cosine. Oh, no. Why did I write cosine twice? The secant of theta equals, and the cotangent of theta equals. So we already know that cosecant is 13/5, which automatically makes the reciprocal 5/13. That's super nice. We also have drawn our triangle. Our cosine is the adjacent over the hypotenuse, and our tangent is going to be the opposite over the adjacent. And these ones you can just flip upside down and you're done. Easy enough. This one's going to be a little bit more difficult because we have a square root in there. We're going to have to figure that out. And we're also told that cosine is negative. So just because we're in cosine is negative, let's just look at our little picture there that we have from before, where it's sine positive but cosine negative. Well, sine positive, cosine negative is that second quadrant, the student's quadrant. So you're over here in quadrant number 2. So you know that the cosine is negative and all the other ones are going to be positive. Anyways, we have to draw this triangle that has a hypotenuse over an opposite. That is to say, we have this is our hypotenuse and this is our opposite side, and we need to figure out what this other side is. There are a couple of options for doing this, but I really think the Pythagorean theorem is going to be your easiest option by a significant margin. So we're going to go ahead and do that. We have our 4 squared plus, I'll label this guy x. X squared is equal to 3 rad 2 all squared. That's going to be 16 plus x squared. When you're squaring something like this, the square root disappears on it and becomes a regular old 2. 3 times 3 is 9. You get 9 times 2, which is 18. And therefore, x squared is equal to 2, and therefore x is the square root of 2. There we go. And then now we need to find sine, cosine, tangent of all these things. In my class, I do not care about simplifying and reducing, but I will show it just in case you have a previous or a future teacher that does. How could you have a previous teacher that, whatever. Cosine of theta equals the tangent of theta equals the cosecant of theta equals the secant of theta equals the cotangent of theta equals. All right, so we're told the cosecant is 3 rad 2 over 4, which makes this 4 over 3 rad 2. Like I said, you can just leave it like that for me. But if a future teacher doesn't want it, you'd have to multiply top and bottom by the square root of 2 over the square root of 2. I don't have enough room for that. But if you did do that, you would end up, what would you? You multiply by the square root of 2 on the top, and on the bottom you have the 2, so with 2 rad 2 over 3. Kind of a weird one for sure. But you can continue on doing the same idea for almost all of these. Now, for the cosine is going to be the adjacent over the hypotenuse. The rad 2's will cancel out. So you have like rad 2 over rad 2, but that cancels out to be 1 over 3, and therefore the secant is just 3. For the tangent part, you'll have 4 over rad 2, which will reduce to 2 rad 2. And cotangent, the upside down of that, which is going to be rad 2 over 4. Whew. Nasty one. This one's a lot easier, though. This one, secant theta is 5 over 4. And the reason why this one's so much easier because we were back to our 3, 4, 5 triangle. So we have a secant, meaning that the hypotenuse being 5, the adjacent to 4, that makes this one a 3. We're told that sine is negative, looking at our little picture. You know what? All students take calculus. Where is sine negative? Sine is negative in the bottom 2. Secant's positive. It's in our third quadrant. Or if you're looking at it, where is cosine? Or fourth quadrant, sorry. Where's cosine positive, sine negative? That's going to be in our fourth quadrant there. We have the sine of theta equals the cosine of theta equals the tangent of theta equals the cosecant of theta equals the secant of theta equals the cotangent of theta equals. All right, so we have our secant is 5 over 4. That means our cosines are easy one, 4 over 5. Oh, I forgot my negative signs in this one over here, didn't I? Cosine's negative. That means that we have negative, no negative there. Okay, we're also told that sine is negative here, so we have a negative and a negative here. Positives for all the other ones. So the sine is going to be 3 over 5. This is going to be 5 over 3. And then we got 3 over 4 and 4 over 3. We only have one more of these. I don't really know how much we need to be talking about it. Cotangent is going to be adjacent over opposite. 5 over 1. Put it over a fraction, over 1 if you need it. You're going to do our little Pythagorean theorem there. I'm going to skip the work for it. It's the square root of 26. Really not much to it. 1 squared plus 5 squared square rooted. And let's go ahead and do all 5. Sine theta equals cosine theta equals 6. Why did I say 5? Man, oh man. Then we have the tangent of theta equals, and then we have the CSC of theta equals, we have the SEC of theta equals, cotangent of theta equals, we got cotangent is 5, and therefore tangent is 1 over 5. And now sine. Sine is going to be 1 over the square root of 26, and again we're putting theta over here. Which makes this one 26. This would be a rad 26 over 26, by the way, if you're trying to do it that other way. For cosine, that's going to be 5 over rad 26, or 5 rad 26 over 26. If you're trying to do it differently. And then secant will be the upside down, or square root of 26 over 5. I think that's it for this video, right? Yep, I'm starting off the last page a little bit later. Have a wonderful rest of your day, guys, and peace out.